Okay. Um, Good. I think it's recording and you have the entire board. Okay. Diogo will tell us about bisimilarity of simple grams.
Yeah.
Thank you. It's the most people we had.
All right. Well, thank you all for coming. So I'm guessing that the point of these seminars is to be more of an informal discussion rather than a formal presentation. So I'm going to tell you a little bit about the problem that I've been working on for a while, some of the progress that we've made, and also what are it's not still completely resolved. So this is still ongoing and unpublished work. So, but I hope that maybe this is interesting to you. Okay. So, first of all, let's get the pen that works. I'm also not exactly sure how much time I should spend. So whenever you guys feel that this is getting boring, you can tell me how to stop. Otherwise, I can just keep talking all day. So the problem is the following. Let me start by telling you what the context-free grammar is. So let's start with a more general notion, context-free grammar, which you guys, I guess, most of you should remember this. So what do you need to define a context-free grammar? Well, essentially, we have to give three sets. So we need to tell what the non-terminals, what the terminals, and what the productions are. Okay. So B is just a set of non-terminals, okay, which I will represent by capital letters X, Y, Z, etc. P is a set of terminals, which I'm going to represent A, B, C, lowercase, and then you have these productions. Okay. And productions are essentially a triple which has a non-terminal X, a terminal A, and some words of non-terminals. Okay, gamma. Okay, so if you want, you can think of this as something in the set V times T times V star. Okay. Also good.
So what is gamma?
Gamma is a word of non-terminal symbols. Okay. So the point is that a non-terminal can generate a word of non-terminals.
Okay. But there's some special structure here. Like normally you have a
Yes.
terminal and non-terminal.
Yes. So this is, I'm skipping some details, but this is the grammar represented in this normal form. Okay. So this is what we call gray bar normal form, and essentially I'm skipping over the details, but you can convert any context-free grammar into this form. Okay. Good. So what the problem is now instead of context-free grammars, I consider specific subsets where these productions are in some way deterministic. Okay. So the meaning is that in general, for each X and for each A, you may have multiple transitions, but in simple grammars, you just have one transition. Okay. So let's say simple grammars means that for each X and A, there is at most one production. Okay, something like that. Cool. Okay, so let me just show a brief example of the things that you can do with context-free grammar. So, for example, let's say you have two non-terminals, X and Y, and let's say from X you can transition to Y by A, And from Y, you can either transition to YY by A or to the empty word by B. Okay. So now let's think about the words that we can, the transitions that we can reach from X. Okay. So if you think about it, if you want to say that X has a sequence of transitions that gets to the empty words, and if you always look at the first symbol to get the productions, what this is saying is that first, when you transition by A, you get Y, and then at Y you can either close this A with the B, or you can get another A. And if you get another A, now you have two Y's to close. You have to close them with two B's eventually. Okay. So essentially, the words that you can use are the balanced words, okay, or balanced strings of A and B. Okay. And now if you think of A as an open left parentheses and B as a right parentheses, this is just like the words of opening and closing of the parentheses that where each left parenthesis is matching right parentheses, right? So this is kind of the kind of stuff that you can do with context-free grammars, and in fact is a simple grammar, because for each X there is at most one transition by A, and for each Y there's at most one by A and one by B. Okay, nice. So now, what is the problem? The problem is that I give you a grammar and I want to study whether two words are bisimilar in the grammar. Okay, and bisimilarity here is a notion of equivalence. So in general, when you have automata, you can think about the languages that they define some way. And then you can think about language equivalence by saying whether these two models of computation whether these two computers compute the same language. Right? Bisimilarity here is a stronger notion. So it's not just computing the same language, but actually there must be a matching between the transitions in both systems. Okay? And this has some motivations in process theory, where you want process not just to be equivalent, but actually to be behaviorally equivalent. So bisimilarity is kind of an equivalence of behaviors.
So bisimilarity is notion for the grammar, not for the language itself.
Yes, exactly. Exactly. That's the point.
Kind of isomorphism.
Yeah. So essentially, a bisimilarity means that you have a simulation in both directions. So one process can simulate the other, and the other process can simulate the other. It's kind of very good.
But that does not necessarily mean they have the same rules.
Yeah, exactly. They do not need to have the same rules. Okay. And I will show you an example of two different grammars that are bisimilar. So what's the point here? So here I've talked about transitions from non-terminals to words, but you can easily extend this to transition between words. Okay. So what you can do is you can define what we call a labeled transition system. Okay. Where if you have a transition from X to some word gamma, then you also have, for any words that start with X, let's say X alpha, you get the same transition to the word gamma alpha. Okay. So the point is that now you have this infinite graph, if you want, where all the nodes are words. Okay. And to find the transitions of the words, you just look at the head of the word and figure out what transitions are from that. Okay. So that's kind of the idea. And finally, once you have this label transition system, then you can define bisimilarity. Okay. Right. Yeah, just change that again. Let's see. Well, we can finish the talk when I run out of time or when I run out of pens. Let's see what happens first. Okay, so here's the definition. What do I mean by simulation? Well, it's just a relation on the pairs of words, okay, satisfying two properties. Okay, so these properties are usually called the zig and the zag. Okay, So one property is that any transition on, let's say, on a word here can be matched by a transition on a word there. And the exact property is the converse. So this means that if, that's that. Let's say if gamma delta is in this relation, okay? Let's say I have two words that are in the relation, okay? And let's say that gamma has a transition to gamma prime. Okay? So behavioral equivalence means that the corresponding process must have a matching transition. Okay, so this means that then there exists some transition from delta to delta prime, such that the corresponding pair of words is in the relation. Okay? So you can call this Zeke if you want. Okay. So if you only have this property, this means that R is a simulation on one direction. Okay. So the reverse property is just flip everything, and then that means that R is a simulation on the other direction. Okay. So what you do is if you take some delta that has a transition to delta prime, then you just do the same thing. Okay. Then there exists another transition such that the resulting pair is in the relation. Okay. And finally, we say that gamma and delta are bisimilar. Okay, and we write this as gamma bisimilar to delta if there exists a bisimulation R that contains gamma and delta. So in a sense, this bisimulation is a witness, okay, that the pair is bisimilar, and we just take bisimilarity as the largest of all bisimulations. Okay? Or if you want, as a union of all bisimulations. Okay. So in essence, what this means is that when you have a simple grammar, you can think of two words being bisimilar if every time we have a transition from one, we have a matching transition for the other one, and this corresponds to another pair which is also bisimilar. Good. Okay, let me show another example.
Wait, okay, so these transitions are happening in different grammars. I get that right?
Well, actually, that really depends. So you can say that they happen in different grammars, okay? Or you can just take the union and talk about this, mega grammar, which is the union of both. So technically here, we are defining a bisimulation on a given grammar. So here we are fixing a grammar, and we are looking about words in the same grammar that are bisimilar. Okay? But if we want, we can think about two different grammars, and we can just say whether some word in this grammar is bisimilar to some word in this other grammar. Okay, and the way to recover this is to just take the union of the two grammars. Right? Just take the disjoint union of the non-terminals of the terminals, and just take the union of the production.
So you're saying that if I have a bisimulation,
Yes.
it has this feature, having two, and I take their union, then it's also a bisimulation. So it makes sense to look at the union of all bisimulations, and that will also be a bisimulation. It's the largest one.
Yes. So we're saying that whether the union of two bisimulations is a bisimulation. I think so.
Because if I have, let's say, if I have a transition from A in one of them, then I will also have a transition from A in the union.
Yeah.
If I have a transition from A in the
union, then it must be in one of the two, right?
it must be in one of the two.
And then you take the matching on either R1 or R2. So these will be either in R1 or R2, so it will be using. So yes, the union of two bisimulations of any collection of bisimulations is itself a bisimulation.
Right, and this is the one that matters.
Yes, exactly. Okay. So let's take some simple example here. Let's say that you have a grammar with the terminals, with non-terminals x and y, such that x has a transition to y and y has a transition to x, okay, by a and by b. And now let's look at this other grammar, or if you want, let's extend the grammar with 3 more symbols, such that a has a transition to b, b has a transition to c, and c has a transition back to b. Okay. So if you want, in this setting, there is a bisimulation between words here and words there. Okay. So in fact, you can prove that x is bisimilar to a. And how do you do it? You just exhibit the bisimulation that witnesses this fact. So in this case, you can think of R as saying, okay, so x must be bisimilar to a. And now, since x has a transition to y by non-terminal small a, then a should also have a transition by non-terminal small a. And in fact, it does. So y should be bisimilar to b. And now we see, okay, now y has a transition to b by b, and b also has a transition by small b. And one goes to x, the other goes to c. So you can just add x and c. So these R will satisfy both properties z and z. And so these will witness that x is bisimilar to 1. Okay, this is not the whole bisimulation, because technically this is a bisimulation about words of non-terminals, not just non-terminals, but you get it. Okay, you just care about finding one bisimulation. Okay. Cool. So now finally, I can state the problem that I want to study. So the problem is, can I write this? Yes.
Can you give an example where this, the bisimilarity requires more than one symbol? Right, so like the 2 grammars and the first one has some symbols, the second one. But like one of the symbols in the top one is bisimilar, never to one, just one, you need 2 in the one or something. You see what I'm asking?
Well, here x needs to be bisimilar to a and also to c. Is that what you're asking?
No, but I mean like the x would be similar to AB.
Oh, I see. I see. Yeah, okay. So for example, you can have something like x has a transition to a to b, okay? B has a transition to the empty words, and A has a transition to the empty word, for example. Okay. So in this case, X will be bisimilar to anything. Okay. So both have a transition by A, right? So this goes to B, and this goes to B, and then both have a transition to the empty word. So the empty word is always bisimilar with itself, right? Vectors, because there's no transitions there. Yep. So the problem that I want to study is I give you a simple grammar. Okay. So not just context free, actually simple, so deterministic. Okay. And I give you 2 words, gamma and delta. Okay. And the question is, decide whether the words are bisimilar. Oops. So this is kind of like the main task that I've been working on for the last few months. Okay. So figuring out whether there are efficient algorithms for this. Okay. Good. So before I get into the details, maybe I wanted to talk a little bit about related work and why this matters. Okay. So what can we say about problems related to this problem? Okay. So first of all, I've already explained that simple grammars are, a subset of context-free grammars, right? And essentially, the type of productions that you allow in either case, these productions often form a non-terminal, a terminal, and a word. Okay. So of course you can extend this up and down the hierarchy, right? So for example, if you restrict that your transitions are only between symbols, between non-terminals, then this is essentially finite state automata, right? So here you have finite state automata. And then conversely, you can push this up to push down automata, okay? And the idea is that in the push down automata, you have like a stack of the symbols and the state, and your transitions may push something onto the stack. Okay. So here, if you want, the type of transitions that you have are, you have a state and some words at the top of the stack. And then after this transition, you get to some state Q, and you might push something onto the stack.
So they're actually equivalent as the languages decided by each are the same, but not as grammars, let's say. Because push down automata decide context-free grammar. Sorry, decide the same languages as context-free grammar. Right? But what you're saying is that as grammars, let's say, as
Yes.
models,
Yes.
in terms of bisimilarity,
Yes.
they're not the same thing.
Exactly. So in terms of bisimilarity, they're not the same thing. Yeah.
So sorry, say again, when T, X, remind me again, T is the stack?
Yeah, so this will be like the symbol at the top of the stack. Okay. And this is the state. Okay, and this will be the new state. And this will be like what?
That's Q, right? So that's a Q.
Yeah, that's a cube. Sorry.
Yep. And then the red and yellow,
Mm-hmm.
and then you have to decide what to put.
Yeah, so this is like
The stack, yeah.
whatever you put after the top of the stack. Say, new top of stack. Okay. Which may be epsilon, right? Which may be the empty word, in which case you just pop. And then you forget about what's there. So I'm not going to work too much on push down automata. I'm just going to say that here there are some results about the bisimilarity, but the complexity is really, really tough. Okay. So it's like this tower of exponentials complexity, the best algorithms that we know. Okay. Here there are some good algorithms that run in, good is relative, but the best ones is doubly exponential time. Okay. So it's actually complicated. Here is where I want to study. And here actually bisimilarity can be decided in polynomial time. Okay. And essentially what you can do is you can start with a guess of a bisimulation that says all the states are bisimilar, and then you can just prune it down as you find witnesses that they are not bisimilar. Okay. So in the beginning you have n square states, and then as you cut them down, eventually you reach a fixed point after n square iterations. So you conclude whether two states are or aren't bisimilar.
So is this bisimilarity in the case of finite state automata? Is this bisimilarity the same relation that when you minimize an automata, right? You have this right? So two states are equivalent, or you give it a name, maybe it's bisimilarity.
Yeah, I think it's,
If and only if, right, if there's a path that leads one state to the final state, then the same path will lead the second state to the final state, right?
I think, yeah, I think it's a similar construction. I'm not sure, because here the point is that for bisimilarity, we actually do not care about final states in that were generated. So, for example, we may have an automata which has an infinite process, that never reaches the final state.
Wait, isn't the final state just something with an epsilon transition? Am I wrong? The next transition.
It depends on how you define it.
I don't know.
I don't know.
Right, because you go from X to Y to and once you finally reach, if you have an epsilon position, that's a final state. If you don't have it, it's not.
Well, I guess it depends, or you can just define a bunch of these states as final, right? And then you just say that the word is generated if you reach a final state.
No, but what I'm
It depends on whether you want a deterministic or a non-deterministic automata.
Oh, I see. But I would guess that if you try to define finite state automata like this using these rules where you have X and Y, right? X and Y would be states. And then you could say that a state is final if and only if the transition X epsilon is there.
Okay.
Right? And then bisimilarity, aren't we just proving right now that bisimilarity is not exactly equivalent to this? Right? Because what would it mean, right? So because epsilon is equivalent with itself, but I presume nothing that doesn't have the epsilon transition. But nothing else, right? And then what does it say, right? So if you have a path from the states anywhere, including epsilon, then right, then the other state, the same path should lead you to epsilon.
But for these states, you don't have the epsilon at the end, like if we have, like it's just you don't have any more transition, so that's here. Yeah.
So bisimilarity is how stronger you're saying? Because I'm just thinking of this algorithm, I think it's Johnson or something that you learn in first course of one theory of computing where you learn automata, right? You have this algorithm that reduces indistinguishability is what we call it, right? You try to find transitions that distinguish the states, right? And then you say, but I guess it's maybe a weaker. What would I mean? Maybe so I guess if two states are indistinguishable. You say that two states are distinguishable if and only if there's a path, at least one state to a final state and the other not. And then you kind of crank this, right? So final and non-final are distinct. And then you keep cranking back, going back to find more distinct states. And eventually you come up with this equivalence relation on the state.
Yes.
I guess my question is whether it's the same relation or not.
Okay, I think I understand this. So there is a problem with that. I think for deterministic automata, this construction works.
But if for non-deterministic, you don't know.
Yeah, but that's the problem. For non-deterministic, it's not. I don't think it is the case. And I mean, there are some examples where bisimilarity and equivalence, are not the same thing, and they work for non-deterministic automata. Okay. And the simple example that there is this book called Bisimulation and Co-induction, Price and Georgi, and the first example that it shows is this coffee machine, okay, which I can show you because I like this example. So let's say you have a coffee machine that you can do two things. So first thing is you can insert a coin, okay? And now after you insert the coin, you can choose whether you want coffee or tea. Okay, let's say coffee. Okay, so if you want coffee, this will give you coffee. Let's say give coffee. And if you want tea, this will give you tea. Okay. So now I will build another machine that is non-deterministic. And so when you put coin, it will non-deterministically traverse to either a state where you have to choose coffee, okay, and then get coffee, or it brings it to a state where you have to choose tea, and then you must get tea. Okay. So in terms of the language equivalence, they are equivalent. Okay. Because they have the same traces. So here you do coffee, C, coffee give coffee, or C, tea give tea, and here as well. But in terms of bisimilation, they are not bisimilar. And in fact, here, when you go from this state to this state, at this state you have an offer of two choices, right? But now from this state there is no matching transition because either you transition to here and now you don't have tea, or you transition to here and now you don't have coffee. Right? So for non-determinism, this is actually, I don't think you can just recover. There's no trick to convert equivalence into bisimility. Okay. For determinism, I think probably is. Okay. And I think that your construction where you just add an extra state might be the trick. Okay.
You're saying that there's a plug-in algorithm even for non-determinism?
Yes, exactly. Okay. Yeah. So the point here is that this, the bisimilarity here, okay, is in P for even for the non-deterministic case. Okay, even for non-deterministic finite automata. Okay. And this is in contrast with language equivalence. Okay, because for language equivalence for automata, we know that this is in polynomial time for deterministic automata, and we know that this is p-space complete. Okay, for non-deterministic automata. So it's actually an interesting result that bisimilarity is a stronger notion, but it remains in polynomial time even for the class of non-deterministic. Okay. Question. Yes.
So, blah, blah, blah. So you're gonna look for an algorithm which is roughly exponential time? Is that what you're
Yes.
doing? Yes. Is there like a lower bound?
No, there isn't. So in fact, I was hoping that I could find a polynomial time algorithm. Right? So far, I've only found a single explanation, right? But I really hope that there is one. Right? And I'll show another diagram that kind of motivates why I think this is the case. So let's go a little bit again about context-free versus simple grammars. Okay. So we have context-free grammars and we have simple grammars. Okay. Let's think about what we know about these algorithms. Okay. So let's go about them in order. So first, we have for context-free grammars, we know that in general, there is a doubly exponential time algorithm. Okay, so this is at most 2x time. And we know we have actually a lower bound here. So this is at least as hard as x time. Okay, this x time hard, and there is a reduction in this case. And this is for the most general case where the language might be unnormed. Okay, I will just talk a bit. I will define what the normed symbol is in a moment. But let me just finish this table. So for the normed case, okay, actually we know that there is a polynomial time algorithm. Okay, and this was showed like all. Okay, and this was in 1996. Okay, so because there is actually a polynomial time for the case of norms context grammars, then you also get a polynomial time algorithm for simple grammars. Okay. So the question is, what can we do here? Okay. So I guess the point of this talk is to kind of motivate why I found an extra time algorithm. Okay. But the lower bounds in this case really requires that you build the context grammar. Okay. So this lower bound is not for simple grammars, it's really for non-continuous. So there is a hope that maybe, this will be followed. Cool, and now I need to tell you what norm is. Yes. So the point is that, these words, they might transition to the empty word at some point, right? So once you reach the empty word, you get no more productions. So you're finished. So we say that, yeah.
Sorry, how much space does it need?
What do you mean?
So it's in X time, but do you need exponential space or exponential space?
Question. I don't know. I don't know if monomer space is enough. I really don't know. I would have to see the reduction.
Because any of that's separable, right? Well, if you show it's in P space and the other is X times R, well, then you kind of separated it.
I see. Oh, you're asking whether this is P space? Yeah, it is.
Oh, very good, then you separated, or they are separated, yeah.
Let's just see the proof. Maybe. Okay. What do we do? I don't know, yeah, it's a good observation. Actually, I'm not sure.
You're gonna show it, right?
Eventually. How much? Yeah. So, okay, even before I go into the detail, okay, norm. What is norm? So norm means that there is a word u of terminal such that gamma transitions by u to the empty word. Okay. And then we say that the norm of gamma is the minimum of the size of the words such that gamma gets to the empty word. Okay.
Gamma, it's a word.
Yeah, it's a word. Okay.
And in the norm grammar, every word has norm.
Yes. So in norm grammar, every non-terminal symbol has a norm. Okay, and then the norm of a word is just the sum of the norms. So every word also has a norm. Yeah. So I mean, if you want,
Can it be exponential or double exponential?
yeah, it can be exponential. Okay.
But the bound will depend on the norm, Sure. But the bound, this key is only if the norm is polynomial or something?
No, this is even if the norm is polynomial, this is exponential. Okay. This key here. That's one problem. Okay. And there is actually, I mean, this paper has a clever trick to handle the fact that, the words might have exponentially large norms, because it will find the patterns, repeating patterns in the expansion of the word.
Okay, so you're saying that if every word has any sequence of transitions that makes it disappear, if this is true for every non-terminal, then it's called a norm grammar.
Yes.
Otherwise, if it's not norm, that means that there has to exist some word,
Yes.
which you cannot convert to the empty word, no matter what.
Exactly.
Oh. Oh.
And I mean, if you care about language equivalence, then you'd say, yeah, I don't care about these unnormed processes, because they kind of like represent non-terminating computations, right?
Right.
But in terms of bisimilarity, you actually do care about these non-terminating computations, about these computations that go forever. Okay.
Because we assume the computational break.
Exactly. Because you want to use this to model processes that in principle may run forever. So that's kind of like the point. Yeah. So if you only care about normed processes, then you could already use the results from Kirschel et al. To show a polynomial penalty. But in our setting, we really do care about the norms. Right?
Are you sure it's relevant?
No, not yet. First, an application. So why I should kind of give some context as to why I started, getting interested in this problem. It didn't just came out of thin air. Okay. So the thing here is that, when I came to school a couple years ago, I started working with Vasco and Diana and Andrea on session types. Okay. So essentially, this is, some type system to model communication protocols. Okay. Let's say model communication. Okay. And there is this language, this programming language that has been developed by the group here at Lasich, that is called Frist, okay, which is essentially a programming language that allows you to work with session types, with protocols of communication. Okay, Vasco is here, so if I say anything wrong, you can correct me. So, what is the point of what is one of the goals or one of the things that you need to have in a programming language? You need to have a compiler. Okay. So compiler is, let's say this is a Frist compiler, is some procedure that, roughly speaking, you give it a process. Then think of a process as a program P, and it gives you a session type, and it will assert whether this process adheres to the session type. Okay, is type checked. Is correctly type checked. Okay. The point is that, if it's not, then you detect this error at compilation time. And so it's better to detect the bug while you're compiling than to detect the bug, 6 months after the code is being sent. Okay, so that's kind of the goal. So the way that, the people here have developed this compiler is they realize that, in order to determine whether a process matches a given type, you need some sort of subroutine that tells you whether two types are equivalent. So there is this type equivalence routine that it's used in one of the rules of the compiler, where you give the two types, and it will tell you either true the types are equivalent or false they are not equivalent. Okay. And the way that this type equivalence algorithm is built is it uses another subroutine, which essentially it converts P and U into two grammars. Okay, towards in a simple grammar, and then it will do this, simple grammar bisimilarity that will give you true or false. Okay, if either true if the words are bisimilar or false if the words are not bisimilar. And it happens that this conversion really is, reflects and preserves equivalence. So the types are equivalent even only if the corresponding words are bisimilar.
The grammar is fixed or depends on the type?
The grammar depends on the type. Okay? So you can build the grammar for T, build the grammar for U, and then compare them. Or I guess in practice, what the compiler does is it first reads the whole program, and then it builds this huge grammar, as it fits in the types, right? It's kind of the idea.
In the near future.
In the near future, okay, that's kind of the idea of how it works. Okay, and now the current status is that this algorithm essentially implements the algorithm here, okay, for a CFG that is doubly exponential time. So with some clever tricks, but that's kind of the idea. So I will show you a little bit how this algorithm works. But the point is, at the moment, the best theoretical guarantee that we have is actually double exponential time. Okay. So the goal is, if we define a more clever algorithm for this stage, then you can have a more efficient compiler, and then you can compile more programs in reasonable time. So that's kind of like the story of how first I started working in session types, and then during this process I somehow realized that there is this problem here, which is also interesting on its own. Okay, good. Questions? Okay. So I hope I motivated you why this problem is important, at least to me. Right? And now I want to give you some ideas about how to prove this. And how do you actually know? What are the ideas that people have thought of when trying to determine whether words are similar or non-bisimilar? Okay. Okay, so first, the first thing that I want to show you is that whenever two words are not bisimilar, there is actually a witness that they are not bisimilar. Okay? And the witness is essentially a path that you take from one word that you cannot take from the other word. So this is, the first. This has been known for a while. Okay? That there is this notion of a witness for non-bisimilar. So how do we define this witness? Well, the first thing is we define bisimilarity up to n. Okay? Bisimilarity up to n. Okay? And this means that essentially you can match any words of transitions of size at most n with the corresponding word of transitions of size at most n. That's kind of the idea. So formally, the way you do it is you define this by saying that bisimilarity up to 0 is the whole set. Okay? So any two words are always bisimilar up to 0. And then if you want to say that two words are bisimilar up to n plus 1, if, and then you have the same two properties, the zig and the zag. So let's say if gamma has a transition to gamma prime, there exists a transition from delta to delta prime, and gamma prime and delta prime are bisimilar up to n, and then you do the same thing for deltas. That's happening. Okay. So the point here is that yeah,
The n, it has nothing to do with the size of gamma and delta, right?
no,
That's just a second. That's the number of transitions.
just the number of transitions. So this kind of means that, like, if you want to decide whether two words are bisimilar up to n, you can just build a tree of all the possible transitions that you can take from gamma in n steps, all the possible transitions you take from delta in n steps, and then you can try to see if there's a match between the transitions at all these levels. That's kind of the idea. So the first observation is that because of this, tilde n is decidable. Okay. And in fact, it's decidable in time, exponentially in n, because to build this tree, at every you have like a tree of steps n, and the fan out is like the number of
We still have to decide how to map, right?
yes, yes.
But that might keep your picture like. I mean, there's many possibilities, but not the map, I guess,
Yes.
right?
But I guess we can take care of that at the same time, because at the end, this is just, okay, so if the grammar is simple, then there's no problem, because there's only one way to map,
Oh,
right? There's only one way to map an A with an A. And if the grammar is not simple, then you can even do it if it's non-deterministic. And essentially, because I told you that the bisimilarity of non-deterministic finite automata is in P, then you can use the same process. So you can essentially build a graph of all the words that are reachable from gamma in n steps, reachable from delta in n steps, and you can figure out if they're bisimilar there. So, okay, I'm not going to go into detail, but I guess that here you can say that this is in O of d to the n, where d is the yeah, let's say number of non-terminals, right? Of terminals. And then, there's some results that say that the smallest n for which this is, okay, I'm jumping a little bit. Okay, the next observation is that
Also in page six, right? Because, I mean, you don't have to store the three explicitly, you just have to do it. Is that push? Or not?
no. You're saying I don't have to store but I think because I can do it in depth research.
Something like I'm asking, yeah, I guess so, right?
I don't know, yeah.
Because, I mean, you can index into the tree using, like, even if n is exponential, like, yeah, right? You can index into the tree, then that's. Or let's say, polygon. So,
Yeah.
you can index into the tree.
So I mean, anyway, this n, the worst n is at least exponential in the side of the grammar, anyways. So this will be a double explanation. Okay.
The n itself is going to be exponential.
Yes, n itself can be exponential. So this will be maybe x squared. Even if you do it like that.
Okay. I mean, I don't see how to do it without storing the entire path.
Yeah. No, for a simple grammar, you could do it because you can just traverse this tree in depth research, right? And you say you go up to depth n and then you backtrack.
But if the depth is exponential, like
Yes.
to the end,
Yes.
you need to backtrack, you need to keep track of everything. You need to keep track of the path.
Yes. Yes. Yes.
So then it'll be exponential space.
Yes.
If n were polynomial, then it would be polynomial space.
Yes.
Good. So, and you're saying that actually that this equivalence relation is the same. If you do it to the end, you get it. Is that correct? You're gonna, this is coming up.
Yes. So the next observation is that actually bisimilarity is just the intersection of bisimilarity up to n for every n. Okay? So I mean, this is kind of a point that we also should prove, which means that if words are not bisimilar, then they must not be bisimilar at some finite depth, at some finite time. That's kind of the idea.
And now there's another wrong in the standard.
Yes, there is. I don't have it here actually, but yes, there is. There is an upper bound which is, exponential in the side of the grammar.
Good. And that's how you get the double exponential.
Yes, and that's how you get the double. I mean, this is just a witness for non-bisimilarity. The algorithm then has a second part, which is also a witness for bisimilarity. Okay? So this tells you, if the words are not bisimilar, then you can find a witness. Okay. But then I should also tell you a little bit about how can you prove that words are actually bisimilar. This is another trick that has been done.
Oh, so you're saying that if words are not bisimilar, there will be a transition of lengths exponential in the center of the grammar, which is possible from one word, but impossible from the other.
Yeah.
Oh, but then it's in max.
Yes.
It's already not doubly exponential time.
What's that?
I mean, you could say maybe it's hard for doubly exponential time, but it's not. It's in max.
Yeah,
Yeah.
because the witness is
Okay, that's. Maybe you can show that it's next part. And then you set it the problem. The complexity of the problem. Right, because they've shown it's X part. X part, yeah, X part, right? Maybe you can show that it's the next part. And then you found the complexity, technically it's next.
no, yeah, that's good.
I mean, you have to look at the X bar proof and see if it can be
Not deterministic.
made for, I mean, maybe it can't, huh? So maybe-
The proof is essentially modeling some, Turing machine that runs an exponential time.
That's good. Sometimes if you do that, then it's just, you just add another determinism.
Mhm.
Because the grammars are, you can add, okay, fine.
Yeah.
But then you have to, okay, all right. So it's an X when it's been proven to be X part. And that's if it's not a simple grammar.
Yeah.
Now there's, so now for simple grammars, you can put
Okay, so I mean, even if we didn't have these exponential upper bounds, then at least these results, the way I've taken here, show that the bisimilarity is at least co-semi-decidable, okay? So these two together means that bisimilarity is co-semi-decidable. So I mean, we can figure out whether the words are not bisimilar by just, increasing the n and just keep doing this search forever and ever until, if they are not bisimilar, then eventually find an n where they are not, that witnesses that are not bisimilar. Okay, so this is why I call this witness for non-bisimilar. Okay, that's kind of it. So now this is the part where I get the heavy machinery, which is how to find a proof that two words are in fact bisimilar. Okay? So this is what we call a witness for bisimilarity. Okay. And so the way that people have worked on this is they discovered something called a basis, okay? And then they defined this notion of congruous up to this basis. Okay, and then they figured out that there always exists a basis such that congruous with respect to this basis is equals bisimilarity. And so this means that the witness for bisimilarity is essentially this basis and a proof of congruous up to this basis. That's kind of the idea. Okay, so let me tell you a little bit about what a basis is. So a basis is just is a finite subset of words, of pairs of words. Okay. So this is like saying that you have a couple of pairs that you kind of assume that they are bisimilar. Okay. And from these, you generate the whole bisimilarity. Okay. So then the first definition or the first thing that people thought about was defining the congruence up to B. Okay. So then you can define least congruence up to B. Okay. And then this is essentially, some relation that satisfies a bunch of axioms, that make it a congruence, essentially. So, the axioms are that if a pair of words is in B, then they are of course congruent up to B. Okay. And any word is congruent with itself. And this is symmetric. So if the words are congruent, then they also, delta is also congruent to gamma. And transitive, so if you have, let's say like this, if gamma is congruent to delta,
small equivalence relation that includes B.
yeah. Also, the smallest congruence, there's a few proof. and delta is congruent to beta, then gamma is congruent to beta. And then finally, this is the congruence rule. So if alpha is congruent to beta and gamma is congruent with delta, then alpha gamma is congruent with beta delta. Okay. So this is kind of the definition of the least congruence. And now an observation is that, for every b, this is semi-decidable. Okay. Okay. Because, even towards, you can just guess the proof that they are congruent. Okay. I'm not saying this is the smartest way to do it. And finally, what we do is we show that if you take B with a certain properties, then this congruence is actually a bisimulation. Okay. So finally, that gives me the
So
definition.
this observation follows by the fact that B is finite, right? So
Yes.
some kind of saturation procedure will eventually.
Yeah, exactly. Finally, you say that B is a self bisimulation. Okay, if for every word for every pair in B, now you have the zig and the zag for these words, okay, for gamma and delta. But this means that if gamma has a transition to gamma prime, then there exists a transition from delta to delta prime with gamma prime congruent to delta prime. Okay, so here what I'm saying is that for every pair in my basis, I can take transitions from both words in that pair, and I arrive with pairs which are derivable, whose congruence is derivable in B. Okay, that's kind of the idea. Now I do the same thing for the Z. Okay, so delta prime, etc. And what's the point of this? The point is that if B is a self-bisimulation, okay, then this implies that the congruence B is a bisimulation itself. Okay, and so in particular, this implies that this is a subset of bisimilarities. So what this means is that to figure out whether two words are bisimilar, I can do one thing, which is I can guess a basis. Okay, let's say I guess a basis, and then I can guess two things. First, I can guess a proof that the words are congruent up to this basis. Okay, and then I can guess a proof that B is a self-assimilation. Why? Because I just need to go for every pair in the basis and every pair of matching transitions, whether this is congruent. Okay, so using the fact that this is semi-decidable, I can essentially use it as a way to build against that words are bisimilar. That's kind of the idea. And finally, the final observation, and this is actually true for context-free grammars. For every context-free grammar, there exists a B such that the congruence actually equals equivalence. Okay, so I mean, what this means is that gamma is congruent to delta if and only if gamma is bisimilar to delta. Okay. Now the problem here is that this proof, this basis, what is the size of this basis, right? So for context-free grammar, this basis is actually exponential. Okay? So this B is exponential in the size of the grammar. So let's say you want to guess an algorithm. What we do? You have to guess over all bases of exponential size, of which there are doubly exponentially many, and then you have to guess a proof that this is actually good for what you want to do. Okay, which again is another explanation. So this is also not an efficient problem, but actually the first paper that showed that this problem was decidable, they did it like this. They show, oh, bisimilarity is close to semi-decidable, and it's also semi-decidable, so it is decidable. Okay. And then there was a sequence of progress that trying to figure out actually the bounds on these first an elementary bound and then a doubly exponential bound. That's kind of how the story went.
You say this V is exponential, you're saying the number of elements of V is exponential and
Yes.
also the word length, each word length also.
The number of elements is exponential. Okay, and I'm guessing that the word themselves also might be exponential. Yeah, also might be exponentially large. Correct. Okay. Cool. So this was all of this is not novel results. This is just a statement of all that has been done. And the first thing that that's kind of novel is the observation that if the grammar is simple, then actually this b is not exponential, it's just polynomial. Okay, so that's kind of taking. So actually, if simple grammar, then the size of b is at most quadratic, where n is the number of non-terminals. N is the number of non-terminals. So essentially, for each pair of non-terminals, you only need one element in the basis. Okay, that's enough. You don't need to consider multiple bases. And this essentially follows the determinism. That's how everything, gets together. Okay. But I mean, this already gives you an idea on how to get the double exponential bound, because we can either guess a witness of non-bisimilarity of size double exponential or a witness of self bisimilarity of size double exponential. That's kind of it.
So I kind of understand that, like, if you give me B, then this B converse is semi-silent.
Yeah.
But then I was starting to think, okay, but is it how efficient would that be? And I have no problem with any of the rules except the transitivity. That would be right, because I mean, the congruence thing only just shortens the word length.
Yeah.
Right, so they become shorter words.
Yeah.
And I think that's not a problem except for this number 4, where you have transitivity. And I don't see why, it's gonna be very long. Could be growing, I mean. Right, you want to show that ultimately gamma is congruent with beta.
Yeah.
Right, that could be because it's congruent with some delta 1, which is congruent with some delta 2.
Yeah,
And this could be like the triply exponentially long thing. And of course, to prove it's semi-decidable, it's not a problem. You're eventually going to get there. But can you prove actually that any proof of congruence? Oh, well, there exists always a proof of congruence whose length, whose size is not greater than the words involved.
Yeah, that's a very complicated question. I don't know. The trick is that actually you don't do this congruence. You, instead of this notion of congruence, you take a gentler notion of congruence that is decidable. Okay, and that is what we call a co-inductive congruence. I will show you a little bit. But the point is that actually you don't need all of this machinery. Okay, you don't need all of these rules. You can just take a smaller notion of congruence. Okay, the only things that you care are that if B is a self-bisimulation with respect to that new notion, then this is still bisimilarity. Okay, and the observation that for every grammar there is at least one basis such that this new notion of congruence actually matches bisimilarity. Okay, and the approach, and I mean this is not my approach, it also has been done before, is to figure out these different notions of congruence that are more tractable than this thing. Like this is kind of like the first idea that came up.
So you could bound, for example, the number of times you do the transitive step, right? I'm just throwing something like, right, because,
That's good,
that's the only issue, right?
yeah.
Because the middle thing,
I mean, here you also need to guess where you truncate
who guess need to guess, but let's say we have a column of space, so we don't, that's fine, right? You're given two words, you maybe you need to break them and you don't know exactly where, but you try everything. That's not a problem. But then the transitivity, I mean, you know, so now I charge you for every step of transitivity in your proof. And now I bound this, let's say it has to be at most whole again. And then would that give you the same? And now you need that under such a weak bounded congruence or something, you still get a characterization. But I'm guessing that's not what you're doing because it's not.
No. I never thought about this approach. That's cool. I did not think about what would happen in that case.
Because then,
Because I mean, I don't even know how to bound. Let's say that two words are congruent. I don't even know how to bound the number of times that you need to use the transitivity. Right.
I see.
I don't even have
Because
a.
if you put it not just in p space, you put it in the form of your,
Okay.
and it goes from close to p, right? Because to guess a proof, what do you have to do? You just, I mean, that's NP now because it's formally bounded proof. And then what do you have to do?
But you still need to guess B, right? The problem here is
So you
guessing
guess
B.
p and then you need to check that p works.
Yes. I mean, checking that B works is just, quadratically many calls to congruence.
All right, and that's next, right? So
The problem is guessing B, right? How do you guess B?
So B, right, so you have the second observation, or the first observation, right, that it's always gonna be, right, so you test if it's self-bisimilar, right, that's some existent, there's some proof of that. And now if under bounded congruence, it's a polynomial size group, right, so that's an NP, right? And now what you need to check? You need to check if there is, to see if two things are bisimilar, you need to guess a B. You check together with the proof that it's bisimilar, together with the proof that these two things are congruent, which again, everything is bounded, so that we can put it in NP. Which is much better than these two. But I don't know, but maybe that's already true for you on the, and then bounded from.
Yeah. Not sure.
Okay, sorry.
Because I'm just not sure. Maybe you really need, exponentially many transitivities to get to where you want to go.
I mean, a proof of that would be proving that it's p-space not If you prove that, then that essentially says you have to follow exponentially long paths, even if you don't need a lot of memory. Really well. Which maybe it would, because if you need exponentially many transitivity, I mean, how do you check, right?
Yeah.
I mean, oh, maybe that's searching for a path, we can still real thing.
And that's also the case that, he was asking whether the pairs here what's the size of the pairs, right? I think that in general, the size of each pair might be exponential. Okay. There's also a problem there.
Okay, I see, if you have to come up. If they're very, very big, then your algorithm is not to find them without trying to.
Yeah. That's not a problem.
Right.
But for the algorithm that I'm thinking of, that I have right now, actually you don't need to generate all of the grammar, all of the bisimilarity. You just need to get, the pairs that you need to prove this particular gamma delta. Okay. And those are always small. Okay, cool. So how are we on time? Should we?
Wouldn't mind.
Okay.
3:30, let's just put 5, would be nice if you could have 5.
Okay, it's up to. To the crowd, I guess. But let me just continue. I kind of wanted to show you the algorithm. Okay. But there's still a little bit better. But now I kind of want to show this technique that I think it's cool, that tells you know what kind of stuff you can do. I mean, how did you come up with the fact that this basis is small? I think that's kind of like a cool idea. So what happens? So how do we find out that this is O of n squared for simple grammars? Okay, where does determinism play a role in making this this problem easier? Okay, so the point here is that let's take two elements x, y. Okay, and now let's think about the question whether x alpha is bisimilar to y beta. Okay, that's kind of like the question that we discussed. And now we split the analysis in 3 cases. So the first case is that the case where both x and y are unknowns. Okay? To make this distinction about whether the symbols themselves are norms or unknowns.
Sorry, I'm not. So you have 2 words, X, Y? No, they are non-terminals.
Yes, they're non-terminals. Okay? And you want to guess, you want to somehow study this equation. Okay, now this is an equation on alpha and beta. These are the variables. Okay, which can be words. And you kind of want to characterize all the solutions to this. Okay? So if x, y are norms, what do we know? We know that we can never reach alpha in x alpha. Because the only way to reach alpha is somehow for x to become the empty words. Okay? So in particular, this means that x must be always bisimilar to x alpha. Because any transition that you do here will be matched with the same transition that you do here, and you will always be, this alpha is never reachable. Okay, that's what I'm doing. And also, y beta is bisimilar to y for the same reason. Okay. So the point is that x alpha is bisimilar to y beta if and only if x is bisimilar to 1. Okay, by transitivity. And you apply transitivity class. Okay, and congruence. No, that's just transitivity, that's enough. Okay, because these are bisimilar to this, these are bisimilar to this. So these two words are bisimilar, even only if these two words are bisimilar. Okay. So what that means is that your basis B, if your basis B has an element x alpha y beta, without loss of generality, alpha and beta are the empty loop. Okay. So this means that if x and y are n1, you don't care about the tails, right? And your basis B, without loss of generality, it has only one pair, starting with x and y. Okay? So this is kind of the goal to show that I think this is at most n squared, at most, yeah, it can have 0. Okay, but if x and y are not bisimilar, then it would not happen. But this kind of already tells you that, okay, if whatever my basis is at the end of the algorithm, okay, if x and y are bisimilar, then it will have the pair xy, and if x and y are not bisimilar, then it will not have no pair of the form x alpha y beta. That's kind of it.
Wait, where X and Y are unknown?
Yes, for x, y, or not.
Unknown, is it?
Yeah, okay. So that's the second case. Let's say x is unnormed and y is normed.
Or you can remove the tail from it.
Yeah. Okay. And now we remove the tails. So and now you want to study whether x alpha is bisimilar to y beta. So again, x is bisimilar to x alpha. Okay. So this is if and only if x is bisimilar to y beta. And now here's the trick. Now, in principle, there could be many betas for which this is the case. Okay? But because the grammar is simple, there can be only one beta. Okay? And how do you prove it? So because y is normal, there is some transition that goes from y to the nth one. Okay. And therefore, let's say, okay, let's suppose that there were two solutions, y beta and y beta prime. Okay. Let's say that there were two solutions to this. Then, because they are both bisimilar to x, they must be bisimilar among themselves, right? So y beta must be bisimilar to y beta prime. But now, this word has a transition to beta by, a sequence of non-terms. And this has a transition to beta prime by the same sequence. And now this is the point. Because the grammar is simple, the only way to match this transition is with this transition because of determinism. Okay? If the grammar was not deterministic, there could be, in fact, exponentially many words here that would map. Okay? And only one of them needed to be bisimilar to beta. So there will be exponentially many solutions to this equation. But because the grammar is simple, after I find out this u, then there's just one derivation possible in both cases. Okay? And so the conclusion is that beta must be bisimilar to beta prime. So what this means is that up to bisimilarity, there is only one solution to this equation. Okay? Well, in fact, I mean, alpha can be anything, but without clause, we can assume it's empty. And beta, there is also many options, but up to bisimilarity, there is only one. So this means that without clause, let's say, if the basis B contains some pair X alpha Y beta, then alpha equals the empty word, and there is no other pair, and there is no other X alpha Y beta prime in B.
You mean because the bisimilarity relation introduced by B, this converse relation, will just having x, y, beta there would be enough to get you x, y, beta prime.
Yes, exactly.
Those are something because of this is the exact thing.
Yeah, because no, it's actually just because, let's say it's just using the congruence, okay? Because let's say you want to prove that x is congruent to y beta prime, okay? So because B is in your basis, you know that x is congruent with y beta, okay? And now, because I've just proven that beta is congruent, is bisimilar to beta prime, then here I can use the fact that beta is, if I can prove that beta is congruent with beta prime, then I can just replace it. I wrote it sometimes by y beta prime.
Wait, but you've proven that beta is bisimilar to beta prime, haven't proven that it's B congruent to B.
Yeah, exactly. But the point is, if your basis is large enough, if your B is, is enough for a self-assimilation, then you just need one of them, prove the other ones.
Oh, I see. You're saying, so you're assuming that B characterizes bisimilation perfectly, and now it has two x, y beta and x, y beta prime. Then you've proven that beta is complete, or if you have bisimilarity. No. So with the, so why do you need B, capital B? Right, so maybe capital B is complete for bisimilarity. But it's only because you have these two rules, x, y beta and x, y beta prime. And you
Yes.
remove one of them, and now it's no longer complete for bisimilarity. So
Yes. Right, yeah, I see. So the point here is that you can kind of advance in the proof by saying that, okay, let's want to say that I want to show that X is congruent to Y. Kind of want to show this. Okay, and what I know is that X is Y beta is in B. Okay, so what this kind of tells us is that now I can reduce this to proving that beta is bisimilar to beta. Okay, but now I need to figure out how this proof goes, right? So the answer is that, as I said, the notion of congruence that we use is a little bit different, okay? And it's actually a co-inductive definition. I haven't told you about co-induction yet, but what I mean is that essentially I allow infinite proofs. So the point is, okay, maybe this proof will
Wait,
continue.
are you just saying that, I reduce the number of symbols,
Yeah.
and so if I just take the word that I still can't prove to be the smallest word,
Mhm.
I can't prove it because if it's with this form.
Yeah, so essentially the point is that I can always apply a rule somehow, okay? And as long as I can always apply a rule, then I'm fine, even if the proof itself is infinite. Yeah, so let's just put a hold on this and maybe when I define the notion of congruence that I care about, this will make more sense. But for now, what I kind of want to say is that, up to bisimilarity, you only need to consider, this solution has only one equation. Well, this equation has only one solution, right? That's kind of the point that I'm trying to make here. Okay. So this is a rule that will be used in our new notion of congruence, and I'm going to call it BPA1. Okay. Why? There's going to be a BPA2. I'll show you. So, but first, let me just finish this case analysis, I guess. And the next case is when both are normed. And let's say that without loss, the norm of X is bigger than the norm of Y. Okay. They're both normed. There is a word. They both have words that both have transitions sequences to empty words. Okay. And now let's look again at the equation X alpha bisimilar to Y beta. Okay, that's kind of the correct. We want to characterize the solutions here. Okay. And essentially, I want to show that there is one solution. Okay. Yeah. I mean, kind of. Okay. Okay. So let's see how this goes. So first, because they are both norms, there is some words Y, some transition, some minimal transition that goes from Y to epsilon. Okay. So now let's think about what happens here. So because the norm of X is greater than Y, this X also must have the same transitions because they are bisimilar. And taking this sequence cannot consume X because X had a bigger norm. Right? So if I play along this game,
It might, but only just.
yeah, it might, but only just. Yeah. But the point is there is some words. Let me choose the one. Yeah. Okay, there is some word. Okay, so the point is that Y beta travels to beta and X alpha travels to gamma alpha. Okay. And again, because the grammar is simple, these must be the unique, matching transitions. Okay. So at the end, I must have these words matching. Gamma alpha must be bisimilar to beta. Okay. So this gives us something. This tells us that this equation that has two parameters, I just resolved that one parameter must be expressed in terms of the other. Okay. So if X alpha is bisimilar to Y beta, then this beta, I can actually just replace it by gamma alpha. Okay. So this means that beta must be bisimilar to gamma alpha, and therefore thus where I put y beta, I can just put y gamma alpha. Okay. And now I have an equation with just one variable, which is this alpha. Okay, this gamma is not a variable because it is the result of taking the sequence of transitions u. All right. Okay. Now I have two options. So this is a very complicated case analysis, but now there are two cases. The first case is that maybe x was bisimilar to y gamma. Okay, this is one option. Okay, it might have been the case that they were already bisimilar here. So then the point here is that actually this alpha could be anything. Any alpha that I put is a solution. Okay, and the solution is characterized by gamma. In this case, the first observation is that gamma is unique. Okay. Why? Because from x and u there is a unique gamma. Okay. And the second observation is that for any alpha, x alpha is bisimilar to y beta if and only if gamma alpha is bisimilar to beta. Okay. So this becomes an if and only. So one direction is easy because from here to here I just proved, and the converse direction is I just take congruence. Okay. Because if gamma alpha is bisimilar to beta, then x alpha, because of this, is bisimilar to y gamma alpha, and because of this, is bisimilar to y beta. So what's the bottom line? If this is the case, so here I guessed what gamma is, and now if x and y gamma are bisimilar, then first of all gamma is unique, and second the solution to this is just I just take any alpha here, and beta must be gamma alpha.
So why is gamma unique? Because gamma is the nth derivative of x, right? So there may be more than one.
Yeah.
Different ones. Okay.
The thing is, you fix a u. You fix a u that brings you from y
It's
to
the number of reductions.
no. This u is actually the transition sequence itself.
Yeah, I said about the number. Okay, go ahead.
So this is a word. This u is a word of the. Okay.
Different you could give you different gamma, but we fixed one.
Yeah, but I fixed one. Yeah, I fixed one. So I mean, yeah, different u could give you different gamma, but actually they will all be bisimilar if this would be the case, because you just take one, and this goes to epsilon, so this will go to gamma or to gamma prime. Okay. So in this case, the conclusion is that if my base is B has some pair x alpha y beta, then I can just take alpha is the empty word, beta is my word gamma, okay. And there is no other pair. Okay. And there is no other pair. Let's call it x, y, beta in B. And the point is that now if I want to prove again that x alpha is equivalent to y beta, what I do is, well, I use the fact that x is bisimilar to y gamma for some for this gamma that I defined here. This is in B. And now my rule would say that this, where is it? This is bisimilar if and only if this is bisimilar. And I get gamma alpha bisimilar to beta. And this is the rule that I apply. Okay, so essentially my congruence. No, this is one. This is one.
So you say your congruence, you're saying that you're coming up with a system of deduction.
Yes.
Now you're giving us the rules of the system.
Yes, exactly. So I'm, building. I'm motivating where this
But am I not right in saying that the length of the word always shortens by the application of each rule?
Mhm.
So there can be no infinite deduction. It becomes shorter, 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 and then it's done.
I haven't, there's one more rule.
Ah.
There is one more rule. And I mean, actually here, no, actually this is the rule. Here the sequence does not shorten. Because we replace x
Oh.
by a gamma. Okay, and this gamma, might be big. Yeah, so this is actually the comparison. So here the sequence itself is not shortened.
But then how we prove that things are similar in the system?
Because
Once they remove, we can-
although it does not shorten, this is somehow smaller than x alpha, in the sense that you can take gamma alpha from x by following a sequence of norm decreasing transitions. That's kind of the point. Okay? Because if these are bisimilar, and because this u, let's say this u was the smallest possible word. Okay, so the reduction from the transition from y gamma to gamma is the smallest possible. Okay, and because these words are bisimilar, then the corresponding sequence must also be the smallest possible. And so in a sense, this gamma alpha is in the canonical sequence that reduces the norm, kind of. Okay, so there is this other technical part that I
The
didn't.
norm goes down.
Yeah, so the
but it
norm
could
goes
be-
down. The word themselves can go big, but the norm also always goes down. So actually, these words that you get must be in the chain of decreasing norm, in this sequence of decreasing norms.
Then that would mean the proofs would be as big as, the height of the proof would be as big as the norm.
Yes, yes,
So that's huge.
yes. That's exponential. Yes.
That's exponential, right? But then you've been in exponential. With why? Or you're saying because the norm
Because the norm is at most single exponential.
single.
That's why I get the
Or but you're saying there's only one way of applying the rule, if you have any word.
Yeah, yeah. See here, there's only one way.
I see.
I mean, here assuming that x is bisimilar to y, because there's only one pair in B for each x, y.
Right.
Okay.
Oh, but then it's just a line.
Not yet, there's one rule missing. Okay, and this is the part that gets tricky. So the point here is that if everything is normed, and now I go back to this case that I showed that when everything was normed, there was actually polynomial time even for context free grammars. And that was the point. The point is that if everything is normed, this is the only rule that you need. And this rule essentially builds you lines. Okay. So you just need to follow this one line. There's just like, this is not a tree that like branches, it's just one single line. And then you can apply some structures, some patterns to truncate this exponentially large line somehow. Okay. The problem is when you have a norm, now I have to include a second rule, which will branch. So each node may have two different paths that you need to find out.
But you just gave me a rule, that's it.
No, because this is only the case that x is bisimilar to y gamma.
Oh, I see.
Okay.
Well, that's the last thing.
Yeah, that's the last year that means. Okay, almost there. Okay, so now let's say that x is not bisimilar to y gamma. Okay. So this means that there is some weakness of non-bisimilarity. Okay. So there is some way to match, there's some transitions from x that will eventually reach a point where y gamma cannot transition anymore, or vice versa. Okay. But now, what is the point? The point here is that I already knew that, where is it? X alpha is bisimilar to y gamma alpha. Okay. So I have this, but I also have this. So somehow these words themselves are not bisimilar, but I can put the tail alpha, and then all of a sudden they become bisimilar. Okay. So how can this happen? Okay. The point is that this can only happen if at some point one of these, either left or right, goes to the empty words and the other goes to something that is non-empty. Okay, and this alpha itself is a norm. Okay, let me show. Let me give you an example. Something like this. Maybe x goes to, let's say A, okay, and y goes to epsilon. Okay. Now here x is not bisimilar to y. Okay. Oh, and let's say A, from A you always go to A. It's a norm. Right? So here the words themselves are not bisimilar, but now if you put an A on both sides, then they become bisimilar. That's kind of thing. We can have this unnormed tail that will somehow create the cycle that you need to recover bisimilarity. That's kind of thing. And that's what we use here. So without blocks, this means that there is some words, some different words. Let's call it V, I guess. Yeah. Such that x goes to epsilon from V, and y gamma with the same word V goes to something else. Let's say some delta, which is not epsilon. Okay. It's either this or the opposite, or maybe this one goes to epsilon and this one does not go to epsilon. Okay, doesn't matter. And so then what happens? Now we go back to this and we apply now sequence V. Okay? So here first we have applied sequence U to derive that gamma alpha is different from beta. And now we apply the different sequence V to derive that x alpha goes to alpha and y gamma alpha goes to delta alpha. Okay. And again, because these words are bisimilar and because the transitions must be unique, the resulting words must also be bisimilar. So I get alpha must be bisimilar to delta alpha. And now because then this must also be bisimilar to delta alpha. And this must be bisimilar to essentially delta infinite times alpha. Okay, and essentially the point is actually delta infinite. The point is that then this alpha is unique. It's just an infinite application of deltas. Because its delta is non-empty, this infinite application is a proper infinite word. So I mean here what I'm kind of using is I'm using this auxiliary result that if delta is different from epsilon and gamma alpha is quite similar to delta.
So this would be an ending node in your proof, a leaf in your proof.
Alpha is unique, essentially. That's the last one.
Right. So this would be a leaf in your proof. If you prove that it's for any alpha and delta, that alpha is equivalent to delta alpha, you're done. Sorry.
No, so the point here is that what I've kind of want to say with this is that in this case, okay, I know I need to study this equation on only one variable, and I have just shown with this argument that this variable is unique at bisimilarity. That's kind of the point. Okay, alpha is unique. So this means that if B contains the word x alpha y beta, okay, in this case, then alpha is unique. Okay, so without clause there is only one alpha. And I have concluded here that beta is bisimilar to gamma alpha. This is before the case analysis, so it's valid in both cases. Right? And beta, which is gamma alpha, is also unique. So this means that if I have a word, a pair x alpha y beta in my basis, then without clause, there's only one alpha at bisimilarity, and there's only one beta at bisimilarity. So it's like I only need one pair. Okay? Again, this uses the fact that the grammar is simple, otherwise there would be exponentially
Oh,
many.
now you're saying you need to prove these two things, that alpha.
Exactly. And now what is the rule of x? Exactly. So the point is that now let's say I have x alpha prime. I want to prove that x alpha prime is bisimilar to y beta prime. And my basis B will have x alpha y beta. Right? And now the conclusion that I've asserted is that, okay, this is only the case if alpha is unique and beta is unique, and therefore if these are bisimilar, then this alpha prime must be bisimilar to this alpha, and this beta prime must be bisimilar to this beta. So alpha prime must be bisimilar to alpha, and beta prime must be bisimilar to beta. And this is finally the second rule, the big gate rule. So that's kind of how you arrive at it.
So these four rules for system of deduction, right? So now you guess B, and you only need, also, there's a few things that you still need to tell me, which is like the lengths of the elements of B, right? They could be somehow polynomial, so that you can guess B. And, but also the depth of this tree should be polynomial, right? Otherwise,
Yeah.
or you should be able to truncate something, which is not a thing.
Yes, exactly. So yeah, so the progress that I've done is I don't need to guess B. That's the main difference because I will construct B as I go along. Okay. So this is also kind of a new idea. So okay, so let's see. The first algorithm, what we did was we guess B, whatever, just traverse this double exponential space, guess something, and if it's true, then it's true. Okay. This other algorithm that works for normed grammars, what they do is, okay, first, let's start with a big B, okay, a large basis, and then we try to refine it in steps. So first we assume everything is bisimilar, and then on each iteration, I discovered that this pair actually could not be bisimilar because the transitions are not provable. So I remove this B. So this kind of like you start with the big B, and then on each iteration you remove the B, right? You remove elements from B. So the new algorithm that I have actually works the other way around. So you start with as few assumptions on B as possible, and each time you find a new pair, if it's something that is not yet in B, you add something to B, right? And then eventually, at some point, when X and Y are normed, now you need to guess. I don't know if X is bisimilar to Y gamma, or if X is not bisimilar to Y gamma. So here, first, there are many ways to do it, but first you guess that you are in this case, and you add this element to B, and then later on you might arrive at a contradiction, okay? When you do arrive at a contradiction, then you go back to the step where we prove this, and now you assume the other case, okay? And now, what's the trick? What's the trick? Here, if you are in this case, then you already have a candidate for gamma. Why? Well, you just take any word, any small word, the smallest u such that y goes to epsilon, and then you see what's the corresponding in x. Okay, so you can construct this gamma from y and x. Here, you have no way to construct because you don't know what alpha and beta are. But the point is because this is in your tree, there is this node that you can use. And so you use that very same node and put it in B. So I'm guessing I can just show you what I have planned is I have an example of the algorithm of derivation. And if you want, I can show you how it works. Right? Instead of giving the algorithm, writing down the algorithm. Okay, sounds fun. Sounds fun. Okay. So what are the ideas? So I call this the basis updating algorithm. Okay. So the first idea is I'm going to use these two rules, the rules VPA1 and VPA2, okay, instead of list columns. Okay, that's idea number one. Okay, why? Because these are in some way more practical. And we don't need to worry about guessing the proof, because it will give you how to build the proof. Right? Either it works or it doesn't. And now, why is it based updating? So the point is, we start with a small b. Okay, so essentially the small b that we start is, we only have pairs x in x. Okay, so the same non-terminal. Okay, because these we always know that they will going to be in b by reflexivity. Okay, so first we just have xx, and we can either add or update pairs. And the third thing is, okay, I've now realized this is really vague, but whatever. I'm just going to say, I backtrack if I need to. Okay? So let me give you an example. I like this example because it shows exactly how to backtrack. Okay? So I'm going to write a very complicated grammar. I want to show, I to determine whether xc is bisimilar to y. The capital letters are non-terminals, and lowercase are non-terminals. So x has three transitions: small a, small b, small c. Okay. What about y? Y also has three transitions. Okay, so far so good. A, B, and C. A goes to epsilon. This goes to C. This goes to B. Z has two transitions, and W also has two transitions. Okay, and now finally I have B, which goes to epsilon, C goes to C, and D goes to B. Okay. All right, so this is the grammar. Okay, I know it's a little bit complicated, but it was the smallest that I could find that has this interesting backtracking idea. Okay, so first we can stare at this for half an hour, figure out whether it's bisimilar or not bisimilar. Okay, but now I'll show you how you derive it. Okay. How does this work? So I want to guess whether these words are bisimilar or not. Okay. So at the first stage, let's say I have the basis here. Okay. So my basis, first it only has the reflexive pairs, y, and so on. So now you go from here and you see, okay, so x and y are not still in my basis. So I need to guess, is this a BPA1 pair or a BPA2 pair? Because both are norms, okay, I have the two possibilities. So because I don't know at first, I'm just going to guess that it's a BPA1 pair.
So when we say, yeah, we're trying to assume it's a BPA1 pair, that doesn't work. What does that mean? What does it mean not work?
So it will not work if we find a contradiction later. It's a pair of words that we know for sure that are not bisimilar.
How do you know?
For example, if one, so here the cutoff is when one is empty and the other is non-empty. Okay, that's it. That's kind of like.
That's where you start. That's where you contradict.
That's a good conclusion. Okay.
And then if you find it, you just fuck it up, like you said on third line.
Yeah, if I never find a contradiction, then essentially I must cycle between pairs that I've already visited, and then when I've finished all these loops, then I can say, okay, they are bisimilar. So here I don't know yet, so let's just guess it's in BPA1. So I add x and y, I need to find some gamma. Okay. But because x and y have the same norm, then gamma might be the empty word. So I can just assume that x, y is the word, is the pair in my basis. So now what that means is that I need to prove that this is a bisimulation. So I need to go through every single transition from x and y, see that they match, and see the corresponding words. So x from A goes to epsilon, and y from A also goes to epsilon. And go epsilon, epsilon. X goes to ZC, and y goes to WC. And C, X goes to epsilon, and y goes to D. Okay, so here I'm already going to find a contradiction, but let's say I do this depth first search, so I don't expand this node yet. And now the other thing I need to do is, because I'm guessing that this is the BPA1 pair, I need to apply the corresponding BPA1 rule. And in this case, the BPA1 rule just says that, okay, if X and Y are similar, I can just cut off X and Y and write this as CC. Okay, this is application applying the BPA1 rule. So maybe I should write it down here. BPA1 rule, in the case that gamma is the empty word, I just get the both tails within the relation.
So what's this ABC thing?
Right?
The ABC, what are you doing with the ABC?
So this is just a way for me to remember
This
which
is not part of the,
transitions I'm taking.
this is not part of the group, is it?
No, it's not. I mean, it's just a label on the edges. So, okay, so the point here is that
All you have to prove now.
at the same time, I need to prove that this basis is a self-assimilation.
Oh,
Okay. So each time I add a new element to the basis, I need to take all the matching transitions and try to prove that they are still in the congruence. So this is kind of like saying what are the descendants that expand by taking matching transitions.
So by BPA1, you need to add X, Y to the base.
Yes.
And now, so now you've done that, so now you also trying to prove that B is self-rising.
Yes.
That's why you have the ABC.
Mhm.
So this ABC thing is from X and Y, is it?
Yes.
So it's following A on X and Y, B on X and Y, X and C, I. And now what you're saying is that just the C would be enough to tell you that B is no longer bisimilar.
Yeah.
So your application of the BPA1 rule is a bad idea.
Yes. But at this moment, I don't know yet.
You don't
So
know.
let me just continue with this. So this, okay, now I need to expand them. Let's say I do depth first search, so epsilon, epsilon. Okay, this is a reflexive pair. I'm done. ZC, WC. Here again, we're not in the basis yet. So I need to go back here and check whether Z are normed or unnormed. They are both normed. So I have to guess either this is a BPA1 pair or a BPA2 pair. Which
So this is the sign, whether it's non.
yeah, you can compute. Yeah.
How fast can you do it?
This is actually polynomial time. So computing the norm is actually straightforward. Okay. It's just just doing some short stuff. So it's not that complicated. Yeah, I glossed over that part.
Sure.
Finding the norm, let's say this is done. This will.
So they're non.
Yeah, so they're norm. Okay, so first I need to guess that it's a BPA1. And because they both again have a transition to epsilon, I can just add the pair ZW. Okay, as the BPA1 pair. And I can do this. So there's two transitions here. A and B. Z, they both go to epsilon. And one goes to XD, the other goes to YD. And I'm not done yet because I still need to. So this was just, asserting that this is still a bisimulation. But I still need to apply the rule, the BPA1 rule that I wanted to apply, right? And then this gives me 16. Okay, so far so good. Yeah.
But now we've done another guess.
Yes, I'm gonna second guess.
So you have like a stack of guesses or?
Yeah, I mean, I don't know yet, but I think the way to implement this will be, just have this 3. And then eventually, if you find a contradiction, you just go up 3. And you mark the nodes whether they are guesses or not guesses. Okay. So once you find a contradiction, you revisit the last guess that you've done.
So you always go.
in B also, you know, that this pair was added because of this guess.
Hmm?
In B also, you have to note that this pair was added to B because of this guess. And
Yes. You have to keep notes of these things. Okay, so this is done, and now here I already have x, y in my basis. So then now I can just apply the rule BPA1 and get to DD. Okay. Because they both go to, no, sorry. Yeah, because they both go to x, d, y, d, and then I can cut off x and y and I get dd. And this is a reflexive, so I'm done. This is reflexive, so I'm done. And this is where I find a contradiction. Okay. You don't need a breath. So what does this mean? This means that my hypothesis that the xy was in BPA1 is false. Okay. So in this case, I call this a partial failure because it means I have to backtrack. But I might still recover by similarity if I apply a different strategy. So what happens is I go back to the nearest guess that I've done, which is here. I delete everything below it and I start again. And deleting everything means that I need to delete every guess that I've made below it. Okay? Whatever. I just delete everything. Now all of this goes away.
So I'm also, one thing it's not super clear to me, is that this could be part of a larger tree, right?
Mm-hmm.
And not suppose that this is okay. But now we go back the tree and now to the right.
Mm-hmm.
Can you now use the things that you guessed on a subtree, which is not?
Yes.
That's strange for me, because that means that if you explore the right tree before,
Mm-hmm.
right, you get something completely different.
Yes. But they will still be bisimilar.
But what if, so I explore the left tree, right, and I make some guesses, and I manage to prove that these things are bisimilar. Does that mean that necessarily I have not created a contradiction elsewhere?
Not yet. You might have it, right?
If I'm going under this tree, right now I go up and to the right, and now I find a contradiction.
Mhm.
But maybe the contradiction was not because of anything
Yes.
that's on this brutal leading back, it could be because of something I did before.
Yep.
So really, it's a stack. You need to store your assumptions as a stack. Right? So it's not, when you backtrack, you might have to backtrack elsewhere on the tree.
No, because if you find a contradiction there, I mean, it depends on the type of contradiction, okay? But if it's a contradiction that like this, like epsilon v, then you can show that, okay, this must always be the case there must be VPA1 node ancestor only, not necessarily another part of the tree. Okay. And then there's also different contradictions that are, we'll see them in a bit. When you find two different nodes that are not both non-empty, but they do not have matching transition. Okay, this is a total failure. This means that there is no way to recover this because one is non-empty, because they are both non-empty and they are both non-matching. Okay. And this type of contradiction, you can
Weakness of non-biasimilarity.
yeah, it's a weakness of non-maximality. You can blow it up all the way to the root. That's kind of the idea.
So you're saying that the only contradiction that you find, you can show either it's a total failure, or it's a partial failure, and this will be solved by changing some guess somewhere from the roots to this number.
Yes, yes. And it's by changing a BPA1 guess by a BPA2 guess.
Oh,
So this means that it's non-reversible. So at first, you always try to guess BPA1, and sometimes at a partial failure, you guess BPA2 instead. Okay? And because you cannot go back in your decision, then there are only polynomially many partial failures.
and there's still a lot more to go than that. So,
Yeah. All right, should I finish the example? Yeah. Are you guys energized still? Yeah.
we're almost done.
Okay, we're almost done. So I'm just going to show you the end of the example. Okay. So I've scratched everything here, And now I'm going to start again. But now I'm going to guess that this is a BPA2 pair. Okay? This means that I need to guess an alpha and a beta. But I already have. It's this pair. So I use the very same pair as my guess. Because I know that if there is a solution, it's unique up to bisimilarity. So I might as well just take the one that I have in front of me. Okay? So now I go to my basis B and I add X, C, and Y, C. Okay, cool. And now I just need to do the three transitions, A, B, and C. Okay. But now the transitions, they must be from X, C, and Y, C, not from X and Y, as in the previous case. Because now I'm taking this entire pair in my basis. So because X goes to epsilon, XC goes to C. And because Y goes to epsilon, YC also goes to C. Now B, this is, I'm going to write it like this, ZCC, WCC. But actually, because C is unnormed, anything after the first C is, I can just reject, right? So there's this extra, very small detail that is, it truncates everything after the first unnormed symbol. Okay? So just not have, this useless stuff. It's just a speed up, it doesn't change the correctness of the algorithm.
But any symbol. So
Yeah, any,
because it just in this case it was just C, so any C.
yeah, any after the first unnormed, because C is unnormed, there is no way to reach the empty word. There is no way to reach anything after this. Okay, so even if this is like a very big word and this is another very big word, I can just take them off. And now finally I have the transition by C. X goes to epsilon, so XC goes to C. And Y goes to V, so YC goes to VC. Right? Okay, now here technically you have to do the BPA2 rule, but the BPA2 rule applies to the same BPA2 pair. It will just give you that C must be bisimilar to C and C must be bisimilar to C. Okay, so in practice, I would say that in this algorithm, when you guess the BPA2, you don't need to put this because it just reflects it always the first time that you guess. Right. Now let me put like this. Okay, so when you apply the BPA2 rule, assuming that you have this pair in your basis, and you want to prove this pair, what you do is you create one leaf for each, this alpha must be equal to this alpha prime, and this beta must be similar to this beta prime. But because you're using this, when you guess it for the first time, you're using the same pair to prove the same pair. Right? So it's like, okay.
But that's just the first time you change. They would take
Yeah.
the X, Y later and then.
Yeah, but the first time you don't need to do this. You don't need to do this application. You can just go along with self-bisimilarity. That's kind of what I'm trying to state there. Okay, so now here this is done. Here again, I need to guess whether Z is bisimilar to W. And I again get these two transitions. A, B, and the BPA1. Okay, so A goes to, what does it do? Epsilon, epsilon. Okay. B goes to XD, YD. And the BPA1 tells me that C is similar to C. Okay. So this kind of important thing. I have to delete ZW. Okay. Because this proof that ZW was bisimilar used the fact that XY was bisimilar. Okay. And that was because, at this point. So I could not have used it. So I have to start again. And in fact, this is important because if I had this in my basis, then here I will incorrectly assume something that is not true. Okay, and now because I have to prove it again, I will find a contradiction. Okay, so let's continue. So now epsilon, epsilon is done. And here, okay, now here is where I use BPA2 rule. Because why? I have XD, YD, and my basis has XC, YC. So I have to use this rule, and I get two different cases. Well, I mean, they're both the same. I have two cases which are both the same. CD and CD. Okay, and finally, I get a weakness of non-bisimilarity. Why? Because C has a transition by small c, and D has a transition by small d. Okay? So these are definitely not bisimilar. And because neither is the empty word, what do I conclude? I conclude that there is no way to fix this. So this is actually a total failure. Okay? And from here, I get that in fact, the words are not bisimilar. So that's the conclusion. So let's just show, now let me just make one small difference. Let's replace this transition by a matching transition, just to see how proof for true bisimilarity would work. Okay? So the proof goes all the same. And now here, what do I do? Because the transitions match, I can guess a new pair in B. And I will guess, because they are both unnormed, I will guess C, D. Right? This was like the first case.
What will the transitions not? You lost me here. You said the transitions not. Yeah.
Because both have exactly one transition by the symbol
Okay.
small c. Yeah, so they match. That's kind of what I mean. When I say transitions match, I mean they have, for example, here the transitions of x match the transitions of y. Because x has transitions by A, B, and C, and y also transitions by A, B, and C. So the sets are the same. The sets of transition determinants.
Before that, can you explain again why does it work behavior for C and D? I guess if you reach there, it means you made some mistake. But why is it that no other way, every way will happen?
Yeah, that's actually a good question. So the point here is that because the transitions did not match, okay, it's not just the case that C is not bisimilar to D, okay, it's actually something stronger. It is the case that there is no word alpha or beta that make this bisimilar. So let's call this incomparability. Okay, so these C and D, they are incomparable. They're not bisimilar, and there is no way to add a tail to make them bisimilar. So it happens that when you find this, you can propagate it up the tree, always to a previous node. So let's say here, I know that these are incomparable. So these must also be incomparable. And now these must also be incomparable. And because they are incomparable, then I can just keep going.
Regardless of which assumption you use.
Yes. Because here I've used BPA1, right? Okay, so BPA1 assumed that there was some gamma such that Z and W gamma were bisimilar. So in that case, even if these were not bisimilar, they will still be comparable because there was a tail that I would assume. Okay, it's a bit trickier in the case of BPA2 rules, and I guess what I've discovered is that let's say this is your tree, okay, and let's say here at this point you had this X alpha Y beta, and you guess that this was a BPA2 pair. Okay, and now you do this, and okay, you're happy. I'm done. And now you go here, and you find this X alpha prime Y beta prime, where you use this BPA2 rule based on this pair. Okay, and I have alpha prime and beta prime. Okay, and let's say one of these finds the total failure. And so this kind of a neat trick in the proof is that you can propagate this total failure up to here, and then your conclusion is that either this or this is incomparable. Okay, it's not, maybe this was actually the one that was the contradiction, and you just didn't discover it here, but you discover it later on. Okay, the point is you don't care. You know that one of these is a contradiction. Okay, and so you can just apply, finite descent, and say, okay, there's always an earlier node that is a contradiction. And eventually you do this enough times and you get to the root node, which is not bisimilar. So that,
When you reach this, you're not just saying they're not bisimilar, you're saying the root, the gamma and delta that you started with are not even compared.
yeah, exactly. So when you find a total failure, you can say more. You can say that the root node is actually incomparable. It's not just bisimilar, there's no way to restore bisimilarity. Yeah,
So, but you could just, for all your guesses, you never managed to prove it, and then you just know it's not biasing. Definitely.
Okay, so I guess I'll just finish with this example. So here what you do next. You add these words, and now you need to take the matching transitions. Now C goes to C, and D goes to D. So you get again CD. And now you've seen a node that you've already seen. So this is kind of like another way to finish stuff is whenever you see a node that equals that, is syntactically equal to some node that you've seen before. Okay. So this is called a loop, and you finish. And I go here. Oh, this node I also already seen this before. Look, this node is reflexive. Done. CVC. This is unnormed, and this is normed. So I need to apply. I need to do expansion. C only has one transition by C, and V also only has one transition to epsilon. So I take that transition and I get to CC, and I'm done. And I've added here that C is bisimilar to VC. Again, because when one is unnormed and the other is normed, there's only one solution after bisimilarity, okay, which is this one. And then at the end of the algorithm, once all the nodes are finished, the B that I have constructed is a bisimulation, okay? And the witness is the very nodes that I've built in this tree. That's kind of how you prove that the yes answer is always correct. All right. So ready for close, so I guess we should call it there.
Cool. So why you've seen the whole key and size polynomial in the grammar? Exactly.
No, because of the applications of these rules can lead to an exponential derivation. That's kind of problem. So I mean, so to prove now that the algorithm is correct, essentially you can prove three things. So first, if the algorithm returns yes, then the words are bisimilar, okay? And the proof is essentially, I just should say that my basis B that I've constructed is a self-assimilation, and the proof is, and the very nodes that all the nodes that I have in my tree, they themselves constitute a bisimulation relation, okay? Because all the transitions that are here, I can always match them with the corresponding one. Okay. The second is if the algorithm returns no, then the words are not bisimilar. And the way to do this is you show that whenever you have a partial failure, you have witnessed that these words are not bisimilar, and you can propagate it to the next guess. And whenever you have a total failure, you can witness that these nodes are not comparable, and you can propagate it up to the root node. It's kind of like two different things that you need to do. And the third is that the algorithm terminates. Okay. And the way to do this is you say that there are at most n squared partial failures. Okay. One for each xy pair. Okay. And now between any two consecutive partial failures, the only thing you can do to the tree is you add more elements to the tree. You increment the tree. Like here, between the start and the first partial failure, I added 2 nodes. Okay. So because at each point you only have one pair in the basis for each xy, the number of increments is also O n squared. So this means that you have at most all of n to the 4 changes to be. Okay? Because have at most n squared partial failures, and between any two partial failures have at most n squared additions. And now between any two changes, what essentially you're trying to prove, the only thing that you do between two changes, between two consecutive changes to be, is you apply these rules, which is essentially trying to find that the words are congruent. Okay.
So in total, there's only n squared part. In total, you're saying.
Yes, in total.
Sorry, I missed that. Why is it?
Because every time you have a partial failure, you change a BPA1 pair to a BPA2 pair. Okay? And once you do this, you never change it back to BPA1. You have already asserted that this could never be a BPA1 pair. Okay? So once you figure that out, it means that you can only have at most one partial failure for each XY pair.
Can't we, because I've done some backtracking, I removed an XY pair, and then it gets added again on some other.
Yeah. So the point is, once you figure out, let's say here, right? Let's say here, let's look like this. That's a good question. So the point is, let's say here, I guess something was BPA1, and here I guess something was BPA1, and then I failed and I decided this is BPA2. From this point on, I know that this could never have been a BPA1, because the only way for this to be switched is because here eventually I had epsilon b or something like that, epsilon delta. You had a partial failure. So once you have a partial failure from here that goes all the way here, you know that this could never be a BPA1. Okay. Why? Because if it was, the thing is, these are not bisimilar, and you propagate it all the way back to here. So these are also not.
So when you say that you fill over there for BPA1, it's not just saying that with the conjunction of every guess and this is not BPA1, you're saying this is not BPA1, regardless of what conjunction that is.
Yes, exactly. Okay. And so maybe later on, I find here a contradiction, and I have to erase these three and everything that goes below it. But then, because I already knew that this was a BPA2 pair, even if I remove this pair in particular, I can remember that this was BPA2 for sure. So I'll never, if I encounter it again, I'll never guess it again to be BPA1. Look, this always is very complicated. I'm not sure how to improve this beyond this point, because now the last thing that I need to improve is somehow figure out whether these derivations are small or not. They're not small, but whether there is some way to exploit some structure or regularities that make it small. But yeah. Okay, I guess, I don't know. Maybe you guys are tired, so let's call it today. Thank you. I'm also tired.
Any questions?